7th International Physics Olympiad, year 1974, IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Message me if interested. My email is fred1996@hotmail.com, or you can use Skype name Eduard F1996. Problem number 3. A scientific expedition stayed on an uninhabited island. The members of the expedition had some source of energy, but after some time these sources exhausted. Then they decided to construct an alternative energy source. Unfortunately, the island was very quiet. There were no winds, clouds uniformly covered the sky. The air pressure was constant, and the temperatures of air and the water in the sea were the same during day and night. Fortunately, they found a source of chemically neutral gas, outgoing very slowly from a cavity. The pressure and the temperature of the gas are exactly the same as the pressure and temperature of the atmosphere. The expedition had, however, certain membranes in its equipment. One of them was ideally transparent for gas and ideally non-transparent for air. Another one had an opposite property. It was ideally transparent for air and ideally non-transparent for gas. The membranes of the expedition had the materials and the tools that allowed them to make different mechanical devices, such as cylinders with the pistons, valves, etc. They decided to construct an engine by using the gas from the cavity. Show that there is no theoretical limit on the power of an ideal engine that uses the gas and the membranes considered above. Solution for problem number 3. Let us construct the device shown in figure 1. B1 denotes the membrane transparent for the gas from the cavity, this one, but non-transparent for the air, while B2 denotes the membranes with the opposite properties, this one. It is transparent for the air but non-transparent for the gas. Initially the valve Z1, this one, is open and the valve Z2 is closed, this one. In the initial situation, when we keep the piston at rest, the pressure under the piston is equal to P0 plus P0 due to the Dalton law. Let V0 denotes an initial volume of the gas at the pressure P0. Now we close the valve Z1 and allow the gas in the cylinder to expand. During movement of the piston in the downwards direction, we obtain certain work performed by excess pressure inside the cylinder with respect to the atmospheric pressure P0. The partial pressure of the gas in the cylinder will be reduced according to the formula P equal P0 V0 over V, where V denotes a volume closed by the piston as a thermal process. Due to the membrane B2, the partial pressure of the air in the cylinder all the time is P0 and balances the air pressure outside the cylinder. It means that only the gas from the cavity effectively performs the work, figure 1. Consider the problem of limits for the work that can be performed during isothermal expansion of an initial portion of the gas. Let us analyze the graph of the function P0 V0 over V versus V shown in figure 2. It is obvious that the amount of work performed by the gas during isothermal expansion from V0 to Vk is represented by the area under the curve shown in the graph from V0 to Vk. Of course, the work is proportional to V0. We shall provide that for large enough Vk, the work can be arbitrarily large. Consider V equal V0, 2V0, 4V0, 8V0, 16V0, etc. It is clear that the rectangles 1, 2, 3, etc. have the same area and that only may draw arbitrarily large number of such rectangles under the considered curve. It means that during isothermal expansion of a given portion of the gas, we may obtain arbitrarily large work at the cost of the heat taken from S surrounding. It is enough to take Vk large enough. After reaching Vk, we open the valve Z2 and move the piston to its initial position without performing any work. The cycle can be repeated as many times as we want. In the above considerations, we focused our attention on the work obtained during one cycle only. We entirely neglected dynamics of the process, while each cycle lasts some time. One may think that in principle the length of the cycle increases very rapidly with the effective work we obtain. This would limit the power of the device we consider. Take, however, into account that by proper choice of various parameters of the device, the time taken by one cycle can be made small and the initial volume of the gas V0 can be made arbitrarily large. We consider only theoretical possibilities. We neglect practical difficulties entirely. It means by taking large size of the membrane B1 and large size of the piston, we may minimize the time of taking the initial portion of the gas V0 from the cavity and make this portion very great. In our analysis, we neglected all losses, friction, etc. One should remark that there are no theoretical limits for them. These losses, friction, etc. can be made negligibly small. The device we analyzed is very interesting. It produces work at cost of a heat taken from surrounding without any difference in temperatures. Does this contradict the second law of thermodynamics? No. It is true that there is no temperature difference in the system, but the work of the device makes irreversible changes in the system, mixing of the gas from the cavity and the air. So that was a solution for problem number 3.